So first of all, thanks a lot for the invitation to this very nice workshop. And the title of my talk is Scrambling and Thermalization in a Diffusive Quantum Many-Body System. And this, I mean, what we're discussing is something which was already mentioned yesterday in the discussion, namely so-called out-of-time ordered correlation functions. Right, and yeah, here's a journal reference for this work and the code that. And basically, so as a motivation, basically one could think about, or what one has in mind, a conventional picture, so to say, of quantum evolution and quantum thermalization is that there is some initial fast relaxation on the quantum level, in the sense that local operators lose their information content, if you want, very quickly, and then there's a long-term diffusive scaling, which is more on a hydrodynamic level, so to say, and this is fixed by the conserved quantities. Okay, so to show this schematically, so this would be our conventional picture, if you want. So there's this fast local thermalization, and then there's this hydrodynamic tails, and this fast relaxation is characterized by a time scale tau, which can be diagnosed by such relation functions. And for example, one knows that for Fermi liquids, this tau scales as 1 over temperature squared, whereas for strange metals, which are not so well understood, it scales like 1 over T. So even experimental findings. This. But now the question is there something, so to say, some additional feature which is intrinsic to quantum systems? And this brings us to this out-of-time order correlation function. Namely, it appears that there's an additional time scale, and this is a so-called scrambling or propagation of quantum information. And it can be characterized exactly by this out-of-time ordered correlation functions. So the important thing here is that there's a commutator here. And this was, by the way, this was posed quite a while ago, but also in the terms of a random lattice model by Alexei Kitaev in 2013 in a talk at Santa Barbara. Okay, and how to think about these things is how can, so to say, this operator V at time 0 influence other operator W at some later time, as characterized by the commutator. And I guess the classical picture would be somehow that you have some perturbation going forward to some distant location, and then you propagate it back and measure how much, I mean, to the initial point, and measure how much this has, so to say, blown up in some sense. So we will come back to this. Is classically this correspond to something like the butterfly effect. Imagine you have a small perturbation, but this the large change. And another way how to motivate this is as a probe of operator spreading. So by writing down the, so to say, commutator expansion of the time evolution operator in mechanics. So just the commutators with the Hamiltonian higher order, so to say. Right? And yeah, so what we set out is, so to say, to measure or numerically use this OTOCs in a model system. And the model we will be discussing here is a Bose-Hubbard model, so interacting bosons on a lattice. And this is just a conventional version of it. So you have a hopping term and then an interaction term by this or prefactor U, right? Action strength and some chemical potential. But the important thing is that we're in the incoherent high temperature regime. So we're at temperatures. So in particular, there are no well-defined quasi-particles. We'll see on the next slide. So if we use the single particle Green's function here, and you see that this decays basically very, very quickly. So it's a little bit hard to see maybe on this plot, but here's the x-axis would be the lattice side index, and the y-axis would be time. And you see after very short time scales, it case to 0. So I mean, the picture would be that there are no well-defined quasi-particles. But on the other hand, if you now measure the OTOC, okay, really exhibits such a light cone structure. And here I've written it in a slightly different form. So if you expand this word commutator, right, you get terms with 4 operators, and I'm just picking one of these terms where which has this like this out of time order structure, right? So you have a Cj dagger of t and then a Ci of 0. So I'm not writing so of 0, but this is basically the operator at time 0, and then another operator at time point c and another operator at time point c. This is you have alternating time 0 and time t basically. And for the plots, I mean, this is just a small detail. We're actually showing the reduced correlator where we have already, which we have normalized by subtracting the density correlation. Okay. So if you plot that, you get this nice light cone structure, and you can see this ballistic spreading, so to say, even in this incoherent regime where we don't have well-defined quasi-particles. Right? And by the way, this there has been also some work which characterizes how this, so to say, wavefront decays over time. So it also has some, or how this scales with time. So there's some, hence basically the exponent depends on the dimension. So here is again this curve is just a cut through the, basically if you want a cut through the plot showing the wavefront, and then this broadens, so to say, time, and the exponent depends on dimension. And for 1D, as in our case, the exponent would be 1/2. So this is like a diffusive broadening, basically. So this plot is from here. And okay, what we did basically is we wanted to study this, of course, characterize these OTOCs in more detail. I mean, this is basically what is the exact speed with which this light cone spreads, for example. And the next slide. So basically, and here we come back to this butterfly effect. One expects that this OTOC has such a form where we have to divide the distance, the lattice distance, by the so-called butterfly velocity v, and in front of that you have the so-called Lyapunov exponent. So this would correspond to an initial exponential growth, so to say. And let's look at the data. So first of all, so here are some curves of this propagating light cone, and we have distinguished between so-called butterfly velocity versus value reaches 20% of its maximum value, and the so-called light cone velocity, and this is just the onset. So this would be the outer fringe, so to say, of this light cone. And yeah, okay, and based on, I mean, there have been theoretical studies, as mentioned in the beginning, where they think that these two things should basically agree. Anyway, in our plots, they don't really match exactly, but we can, I mean, we can just show them here. So the continuous line would be the light cone velocity, and the dashed line here is the butterfly velocity. And the lower bound for this, a theoretical lower bound, is the Luttinger liquid velocity, and this is by this errors. So at least this agrees with the lower bound. So our curves are have this bound. And if you look now at the onset, so basically what defines in our case this Lyapunov exponent is this initial exponentially growth, so to say, of this OTOC, right? And by that we can extract the Lyapunov exponent, and we show this in this plot. And we have divided this by 2 pi t temperature, because this is a theoretical bound on the Lyapunov exponent. So in theory, so to say, based on, and this comes from, by the way, from holographic duality. So the theoretical upper bound would be 1. Okay, so strange if this quantity would be above 1, but in our case, it's well below this upper bound. So this bound might not be saturated. Sorry? I mean, this is demonstrated here. It's basically just the onset where the outer fringes of this light cone. So we just, I mean, this is in this work is determined numerically just by the shortest time where you have some noticeable deviation from 0 if you want. Sorry? Yes, actually, this should be, I mean, we haven't, that's a good point. I mean, I guess it should be, but we haven't quantified directly in this work. So, the theoretical or connection to theoretical work would be via this Hutchinson-Litchi here. That's a good question, yeah. I mean, I guess that's a picture behind it, yeah, something like that, yeah. And okay, now finally, we can also characterize or look at this diffusive scaling, what I mentioned also in the beginning. So, I mean, so far we have looked mostly on the initial time scales, but now in the longer time scales, one expects that there's a, you have this, so to say, on the microscopic level, such a diffusion equation for the conserved particle number, so n would be the particle number, and this would correspond to such a Gaussian scaling of the density correlation function. So the Cn here is a density correlation function, and here is, which is shown here in these plots at 2 different temperatures. And here again you see a difference between temperatures. So basically, left one would be at relatively low temperatures, and this shows such a more like a ballistic behavior, whereas at higher temperatures you see, I mean, this corresponds to a diffusive scaling, and we quantified this by measuring the density correlation function at, I mean, along the origin, so to say, I mean, at lattice site 0 or distance 0. So if you plot this, I mean, this is this plot basically, and the high temperature is a red curve. And I mean, okay, from the data, it's not totally conclusive, but one would think that this matches with the expectation in the sense that it's such a diffusive 1 over square root t scaling over time. And for these low temperatures, I mean, this just pays very quickly, but I mean, so to say, theoretical expectation would be such like a ballistic behavior corresponding to a 1 over t decay, such a correlation. But this is already in the long-term limit, so to say. But we could also extract this from our simulation. Right. And what I also want to mention, basically, what we try to do is come up with a experimental protocol for optical lattices. And okay, I don't want to go into too much detail here, but basically the idea would be that you have 2 copies of a chain of atoms, so to say. So the copies are shown here, and this upper part is for obtaining the Green's function in the experimental protocol. So the idea is to perform local interferometry between 2 neighbors here. Basically, this can be realized with a beam splitter. So the idea would be that these the tools for this protocol are already available. And then when it's a time run, so to say, after final time one again from the local interferometry at a different site in general. And then if you measure the density difference, this basically corresponds to the Green's function or the relation or the density. It's a slightly different quantity, but it's here it's exactly our Green's function. And for this OTOC, I mean, the interesting thing is you can do something similar, but the trick is basically to do a forward time evolution and then a backward time evolution. Okay, so the first part here is the same as for the Green's function. So you first of all apply a beam split operation and then let the time run, so to say. And now the point is to flip the sign, if you want, of the Hamiltonian. So now we go backward in time and again use a split operation at the original site I, and this gives you a quantity which is analogous to the out of time ordered coordinate. Right. Yeah. Yeah, but it's, I mean, the trick is that you can kind of compare these two things by having two copies. I mean, but it's, I mean, I guess, I mean, the point is that you initialize them in the same kind of state. Like as if you have two copies, but you perturb or let them interfere a little bit, and then let the time evolution run. But I mean, this protocol here is kind of reminiscent of the classical picture, which one has that you go forward in time and then you go backward again. Okay, so this is exactly what one has in mind for this. Yeah. Yeah. Okay. I mean, basically one can. This is like a optical interferometry, and okay. I mean, I can discuss this later, maybe, but it's like a unitary operation which connects to at the side space. Sorry? Yeah, exactly. And okay, in the last part, so to say, I want to say a few words about the numerics, and which is a part where I was mostly responsible for in this work. And okay, so basically used tensor network methods, which are, I would say, the workhorse in computational physics for quantum systems. Sorry? Not really, as far as I know. Not yet, but yeah, would be interesting to see that. Yeah. Right. So, okay. I mean, I can't explain this all from scratch, but of course, in physics, these tensor network methods have a long history, and I mean, basically DMRG, right? And this is, I guess, a method of choice for 1D quantum systems, at least if you don't go to too long times, basically. And okay, anyway, so just to explain the method a bit, what this represents here is the tensor, and each X, so to say, is an index, and we have like two pairs because this corresponds to a matrix, basically, if you want, like a unitary operator on the whole quantum system. And okay, we need two legs because one, so the lower row is, so to say, for the ingoing part, and the upper row would be the outgoing part. And if you imagine, you could, I mean, in principle, you could just contract this upper and lower indices to one large index, so to say, and then it's just a matrix, right? Because you have a tensor with two indices, and this is just a matrix. So that's just linear algebra, basically. But you already see that the tensor on the left is, so to say, I mean, tricky to handle if you just do a dimension counting. So, for example, if you have, like, let's say 3 degrees of freedom per lattice site, 5 legs correspond to 5 lattice sites. So the x direction would be lattice sites. So you have 3 to the 5. They have a 3 to the 5 times 3 to the 5 matrix already, right? And this would be still fine. But if you go to, let's say, 50 or 100 lattice sites, you can't even store this on a computer, right? So I mean, doing this directly is not feasible for larger lattice sizes. And the idea of this tensor network method is to approximate the left large tensor by this by on the right, basically. So each blue dot is blue circle is again a tensor, but now you can handle it because it has only 4 legs, so to say, and the vertical legs will correspond to the physical dimension, and the horizontal legs to the so-called virtual bonds. Okay, and okay, so the idea is if you were to contract this so-called matrix product operator along the virtual bonds, you again get a tensor of this form on the left, but the point is that you never actually contract that, so you always leave it in form, basically. Okay? And there have been even some proofs that at least for short-range Hamiltonians and for the ground states of short-range Hamiltonians, these tensor networks or matrix product states are, so to say, approximation to the ground state wave function. Also, it all is based on the assumption or on the fact that these dimensions along these virtual bonds don't grow too much. Okay, this is the idea behind it. And of course, you can make this an exact identity by just allowing these virtual bonds to be large enough, but then the purpose of this whole approximation is lost, right? What I want to show you here is basically two nice tricks to help the numerics. And the first one is just a rewriting of such an expectation value. This was tested by Thomas Bartel in 2013. So okay, so the first line is just a definition, right? So basically we have a thermal average. So here is e to the minus beta h thermal averaging, and the term in the bracket here would be just a time evolution of this number operator at site L, and here is a number operator at site J. Okay, and now you can just, this is just by reshuffling these exponentials, you can rewrite this exactly in this form. Okay, we use that Hamiltonian commutes with itself, so we can just reorder this matrix exponentials a bit. But the point is now, basically we're exploiting time translation invariance. That's what it is. And if you look closely, what this means is, so to say, that we time evolves the term in the middle up to t half, and we time evolves the term in the middle here up to minus t half, so backwards in time. Kind of makes sense. It just corresponds to saying that this correlation function at t0 is the same as correlation function at t half and minus t half, right? We've just shifted it by t half. But for the numerics, this is a good thing, so to say, because you can, effectively you don't have to do the time evolution up to such, only up to half the maximum time. So if you think about this, what I've mentioned here, these virtual bonds, these tend to grow as you time evolve, and of course this is advantageous if you don't have to evolve so long, basically. Right? Right. And the second trick I wanted to mention is, how to, it's basically already implicit in these formulas, namely, when you have such an expression, you basically do the, you could compute this in two ways, right? You could just try to time evolve, apply the e to the it of h by let's say a trotterized time evolution forward in time, and then go backward in time by this e to the minus it half h. But the point is that you basically do these things in parallel, so to say. So okay, so what I did here in practice is just even odd splitting and trotterizing. But in this method, you always, like what you do in practice, you apply such unitaries from the top and bottom basically. And but this corresponds to like a Liouville time evolution. So you do this basically simultaneously. You have a U and a U-Decker inverse basically on simultaneously on two sides. And okay, okay, now comes the, I mean, why does this make sense? And the idea is basically that you only increase your virtual bond dimension, so to say, at a lattice site where you have applied this local operator here, for example. Okay, so the point is, like, if you, like, just for 1 second imagine this nj is not here, I mean, there wouldn't happen anything, right? Because you can just commute the e to the minus ith to the minus beta h, and then two unitaries would just cancel, right? So you don't do anything. And correspondingly, I mean, the exact version, this virtual bond dimension shouldn't grow at all, right? If you hadn't this local operator. Okay, but anyway, so the point is, since if you use this scheme, basically the virtual bond dimension only grows in the neighborhood, so to say, of this operator. Okay, this is the point here, that you only, I mean, if you're still far away, I mean, this is basically how the bond dimension grows in time schematically. And if you're still far away, it's still not affected by basically by this operator. That's yeah, that's the idea behind that. Are there more questions on that? So I mean, and by the way, for this work, we used a cutoff in the occupancy. I mean, basically for the Bose-Hubbard model, you would have could have an infinite or arbitrary large occupation per lattice site, but here we only used up to, I mean, just 0 occupation 1 or 3, so 1 or 2. So we had 3 per lattice site to manageable, so to say. And yeah, that's basically it. So I want to thank my collaborators for this work, Honorable Board, Manuel Endres, and Michael. Yeah. Yeah. Yeah, okay. I mean, I guess the intuitive picture behind this would be that at low temperatures, one is like somehow approaching an integrable model somehow. I mean, this would, I guess, from my perspective, this would be, I don't know, maybe there's a explanation also. But I mean, at high temperatures, you really see this. But we also didn't know beforehand which temperatures exactly to expect what. Yeah. Yeah. Sure. Yeah, right. Yeah. So the idea would be, yeah, to use a beam splitter in this case, and this, I mean, okay, I mean, Manuel Endres is expert on this, but can, so to say, interfere the local sites at by such an operation. And I mean, we can also write, I mean, we've written down like a unitary gate basically to two sites, and then let them interfere, and then let a time evolution run, so to say. But the point is that you basically create, or you start out with 2 copies of a of a on the lattice system. Okay, that's a trick here. Yeah, actually, I'm 100% sure how this is done in experiment, right? So maybe you can, but it's kind of a bit operating. So I guess yeah, what you say, you would get or something.
Okay. On the numerics side.
Yeah, I guess I mean, right, that's a good question. So here, of course, what makes it more tricky is that you have this per lattice side, right? So doubles your local, I mean, squares your local dimension, of course. And right, it's a ground state. I would use a matrix product state instead of an operator. So I guess this is numerically this is simpler. Yeah, actually, there has been some work by Frank Coleman, for example, that I mean, so like an alternative method how to do this would be with a purification. So you basically you start with a matrix product state, but on a larger Hilbert space if you want. And the idea is if you trace it out, basically you get such a matrix product operator, or trace part of it out. And the nice thing there is that you have still some degrees of freedom in this virtual Hilbert space, auxiliary Hilbert space, which you want to use as a purifying it. And then so they suggested that you use some unitary transformations, which you don't see in the physics. These are just on the auxiliary system to kind of reduce virtual bond dimension. So there are some tricks which you can play. But here I just use this kind of, I would say, straightforward matrix product operator. Yeah, that's a good question. Yeah, and by the way, I also used like particle number conservation as a, I mean, just to reduce the dimension here.
Questions. Well, if you took a
So I mean, first of all, this is non-integrable, right? So yeah. That's a so you say it again. What was your question in the integrable? Yeah. Well, I mean, these are kind of, I would say, closely related. So in the sense, we just define the light cone velocity as slightly different as the onsets. So as long as you have something, right, some kind of feature, you would have both in some sense, right? You would have expected to have a butterfly velocity and a light cone velocity. I mean, but I mean, actually, yeah, admittedly, I don't know. I mean, I don't have a good picture what would happen in the I'm not actually aware right now of studies which tried it in the integral. But wait, there should be some studies also which tried it for the double case. I only know that, I mean, other people have. I think so, right? There should be some work on that also. I mean, I just know some works which used, instead of such a Bose-Hubbard models, they used actually really random unitaries. So this would be the extreme case of randomness, if you want, where you have just, yeah, if you really apply random unitaries in each time step. And also they can even do some theoretical estimations and theoretical work on this. Not only numeric, but also numerics. And then which I mean, what is diffusive is a density correlation function, but this is unrelated to this one. Oh, right. Yeah. So this, yeah, this is again a different story. I mean, right. So this just corresponds to the, if you cut this along this line, basically. So it's just how the if the transition from the maximum value would be 1 here to 0, how this transition basically, yeah, this transition, how this broadens with time. But this is, I mean, this doesn't mean you are in the diffusive time scale in the sense of the hydrodynamic description of the system. This is something different. This is just related to the transition here. Yeah, right. I know this might be a little bit confusing. So this is not related to this diffusive regime, long time regimes. Yeah.